Seems like most of folks are here, so I'm going to go ahead and get started. I just wanted to start out class today. I know a lot of folks have been emailing me about the photometry project, but I wanted to say that I'm really happy to see all of the hard work that you all are putting into this. I'm very proud of you. You've learned a lot in these past 7 weeks, 6 weeks. So I hope you realize that. I was thinking, I was kind of comparing what you all have done to what the Wyoming REU students do, which is kind of similar. So they have 10 weeks in the summer to pretty much completely devote to astronomy research. And they do about the same amount of work that you all did on top of all your other classes. So they also observe their galaxies, which we can't do because we don't have a telescope. We're not in Wyoming. But you did a lot of that work. So just as you turn it in, as you wrap up, just like make sure you pat yourself on the back and that you understand that, just a reminder that astrophysics is hard stuff. And if it's easy, then I'm doing something wrong probably. So you all are smarties and should be proud of yourselves. So I wanted to start out by saying that was true. And please do, if you still are running into issues, please do get in touch with me as you finish it all up. Or if you need an extension or whatever else, that doesn't make me less proud of you. It just means that you are doing a hard thing and you need a little extra time. So please do not be afraid to ask. Okie doke. Also, a few people have turned in tests. If you haven't, that is due Thursday. But again, I am available on email if you have questions about that. Before we jump into Spectra, does anyone have any questions I should answer? Sweet. And then again, never be afraid to ask me questions if you run into issues. That's what I am here for. And you guys are really helping me learn more about this project if I want to do it again. So I'm learning a lot too, and I'm excited about that. But today we are going to kind of start shifting gears from talking about photometry to talking about spectroscopy. As we do that, the first thing we're going to look at is spectral energy distributions, which are kind of the spectral energy distribution fitting, which is kind of the step between spectroscopy and photometry. So we're going to use photometry to try to model spectra. And we'll talk a lot about that, what that looks like, and how we can do that. So this is my bit of silliness for y'all. When I Googled galaxy rainbows, this was one of the pictures that popped up. So Space Llama Galaxy Rainbow. The cosmic llama is watching over us as we begin to talk about spectra of galaxies. But the reason I was searching for galaxy rainbows is because that's kind of what spectra of galaxies are. We're taking the light from our galaxy and we're putting it through a spectrometer to see how bright the galaxy is as a function of color. We can learn so much from spectra, and that's what we're going to spend the most of the rest of the semester talking about, all the different ways we can learn about what's in a galaxy based on what its spectra look like, what the galaxy is doing. But spectra are observationally costly. So the SDSS spectroscopy survey, every spectra takes a 15-minute exposure. And that's because kind of the bucket of light, so when you do photometry, you're saying, I want to get all the light from this source from like 3,000 angstroms to 4,000 angstroms. But when I do spectroscopy, I'm saying, I want to see the light at 3,000 angstroms, 3,001 angstroms, 3,002 angstroms. So you're kind of spreading the light out so it looks a lot fainter, so you have to do a longer exposure to actually get good data. So with photometry, what would take 11 seconds in spectroscopy takes 15 minutes. So that's why we want to have these ways where we can get at all the information contained in spectra, maybe without actually doing any spectroscopy. And that's where SED fitting is going to come in. So we can use photometry, so what you all have done, to try to model a spectra, to get a good idea of what's going on in the galaxy. So that's what we're going to talk about today and next class, and this is going to be a big part of your spectroscopy project. So I will talk a lot more about that next class, I promise. But it's something to kind of look forward to that you're going to get to do yourself, is spectral energy distribution fitting. Sorry. So what SED fitting is we make a model of what we expect a galaxy's spectra to look like. So that's what this blue line is here, is a model of a galaxy spectra. And then we take photometric measurements, so what we've already done, and we fit those measurements to a model. So we say if our galaxy is this bright in the infrared and this bright in the visual and this bright in between, what is a spectra of a galaxy that fits that model pretty well? And then what can we learn about that galaxy from this best fit spectra? So today what we're going to focus on is actually making these models. So what goes into predicting what this curve looks like. So once we know what our curves should look like, then we can take our photometric points and try to find the curve that fits those best. So that's my first question for you all today. If we want to make our galaxy model, what do we need to account for? So in other words, what in a galaxy is emitting light? You can put it in a chat or unmute yourself and shout it out. What should we be worried about? So Maxwell, very good. The first thing we should be worried about is stars. Ethan pointed out, yes, we also need to worry about dust. Is there anything else? One more thing, but we'll work through all of this. Stars, dust, what else might emit light in a galaxy? Gas, yes. So those are our three things that we're going to need our model to account for. So we're going to need to model starlight, we're going to need to model dust light, and we are going to need to model gas light. Sorry, yeah. So let's start by thinking about stars. So this is going to be the first component of our SED, is going to be stars, and we're going to model starlight by using simple stellar populations. So these are called SSPs, sometimes they're also called SPSs, I don't know why, but we're going to call them SSPs. A simple stellar population is the predicted light from a set of stars that are all the same age and all the same metallicity. Now, in a galaxy, we don't really expect all of our stars to be the same age or the same metallicity. So this is a simplified model. A lot of SED fitters are going to take multiple simple stellar populations and add them together. So we're going to say we're going to have a set of stars that are 5 million years old and a set of stars that are 10 billion years old. So we'll have two simple stellar populations added together. But we're going to kind of focus on making one simple stellar population because that is going to be difficult enough. And so we're going to think about what goes into that. And then our SED fitters will kind of take that information and build on it to get a more complete idea of what's actually happening in a galaxy. So simple stellar populations predict the amount of light as a function of wavelength. So the flux as a function of wavelength, the spectra of a group of stars. What we need to know about these group of stars to make a simple stellar population is we need to know their age and we need to know their metallicity. So those are the two main things that are going to determine how much light we expect from a group of stars. So how old is the cluster of stars and what is the metallicity of this cluster of stars? So the output of a simple stellar population is going to look like flux at a specific wavelength probably they don't have wavelength there, but flux at a specific wavelength as a function of time, so a function of age, and a function of metallicity. And what we're doing is we're going to sum up from our lowest mass star to our highest masses of stars, the flux from each of those stars. So the flux of one star multiplied by the number of stars we expect for that mass. So the flux of a star, which is going to be determined by the temperature, the mass of the star. So those are kind of the temperature, which is going to also be determined by the mass, sort of, since we're working with HR diagrams, sort of kind of things. And then the surface gravity of the star is also going to go into this. So that's what's happening here. And that's going to tell us how the star looks as a function of its age and also its metallicity. So then we take that and we say, okay, if for all of our 0.1 solar mass stars, we expect there to be about 100 0.1 solar mass stars. So we multiply the flux of 1 0.1 solar mass star by 100 to get that, and then we integrate over all of the stellar masses we're including. So there's a lot in this equation. We're never actually going to try to solve it ourselves. We're going to let the models do that because it's very tricky, but I just wanted you to see what the models are dealing with. The other thing I wanted to point out is that the upper limit of mass is a function of time. Why would the upper limit in mass be a function of time but not the lower limit? So relativity, not quite. So over time, what's going to happen to our high mass stars?
Like big stars die faster?
Yeah. So big stars die faster, little stars live forever. So our lower mass of stars is going to be pretty constant regardless of how old our stellar population is. But our upper mass star is going to depend on how old our stellar population is. A young stellar population might still have O and B stars, very massive stars, whereas an older stellar population won't have those anymore. Maybe the highest stellar mass will be an A star or even an F or G star. So maybe if we're looking at a 10 billion year old simple stellar population, our upper mass limit might be 1 solar mass, whereas if we're looking at 5 million year old stellar population, we would expect that to be hundreds of solar masses. So that's the basic idea. We want to sum up all the fluxes from all of our star models to get a total flux for all the stars in a galaxy and get a model for that using a simple stellar population. So besides all my rambling about what was in that equation, there are 3 things that go into modeling kind of the F star and the sigma m, so how many of each mass star there are and what the different fluxes are going to be. And those are isochrones, so how do the number of massive stars change with time? So how is this a function of time, this value here? An initial mass function, which we've already seen, it tells us how many of each mass of stars we started with. And then a stellar spectra sample library. So what is the flux of each type of star? So let's look at some of these things. So the first thing I said we needed was an isochrone. So isochrones are going to be our kind of HR diagrams as that show where stars will be as a function of age of the simple stellar population. So a young group of stars will have a lot of these high temperature, high mass stars. We'll see some blue and red supergiants. As we look at older and older populations, we run out of high mass stars, high temperature stars, and we end up with a lot of dwarfs. We end up with stars on the red giant branch, on the asymptotic giant branch, and just different levels of population. So the isochrones tell us what types of stars we should expect in different simple stellar populations at different ages. And if we can make simple stellar populations of different ages, the really cool thing is we can use the SED fit to try to guess how old the stars are in a galaxy, how long it's been since there was a major burst in star formation. So that's our first ingredient in our simple stellar population, is our isochrone. The second ingredient was our IMF, our initial mass function. So this is this graph we've seen before, where we're predicting how many stars there are as a function of mass, with kind of the expectation there will be a lot of very small stars and a few very large stars. So there are a few different models. The initial one was that salpeter, which just says it's kind of a line in log space, but we've adjusted that now with the realization that at some point you can't get, an infinite amount of 0.01 solar mass stars. That doesn't make sense. So you need to have a turnover at some point, where when we get to very small stars, instead of just going on forever, we level off. So this tells us how many of each mass stars were there when the stars were born, and then we use the isochrone to age that, to figure out how many stars we would expect to see as this population ages throughout time. So ingredient number 1 was isochrone, ingredient number 2 was IMF, ingredient number 3 is a spectral library that'll look something like this, where we see what we expect, the spectra we would expect from different classes of stars. So different masses, our low mass stars, our dwarfs down here, our high mass stars and giants up here. We can then add these up to make our simple stellar population. So if we expect there are 100 M dwarf stars, we would multiply this flux by 100 and add it all to, and then add that to, maybe there are 10 G stars in our galaxy. There's going to be more than that, sorry. But then we'd have 10 times this, plus 100 times this, plus maybe a few times of this, and you end up with your spectra of this group of stars. That depends on how old it is, how many of each type of mass, how many of each type of star there are, and what the metallicity is. We're not going to worry too much about how that affects it, because metallicities are very hard to measure with SEDs and are typically wrong. So metallicity we're not going to worry about. Age we are, because age we can actually model pretty well. So that's our 3 ingredients for our simple stellar population. Our isochrone to figure out how many stars there will be of each luminosity class as a function of age, our IMF to figure out how many of each star we started out with, and then our spectral library to figure out what we would expect the spectra to be for one of each of those stars that we can then add up to get a big group of stars. Anyone have any questions about that? Sorry. So once we add all those things together, what we end up with is a simple stellar population. Sorry, I think I cut off the y-axis in my screenshot here. This should be wavelength. So what we can see is younger ones are going to be dominated by blue and UV light, because they're dominated by those O and B stars that are really, really bright, even if there aren't many of them. Whereas older simple stellar populations, once this is 10 billion years old, are going to be more dominated by dwarfs and smaller mass stars that are lower luminosity, lower flux, but will live forever, essentially, or longer than the age of the universe at least. So that's how we get a model for the light from the stars in the galaxy. The next thing we have to worry about is our dust. So dust is going to both emit and absorb light in a galaxy, and we need to consider both of these things when we create our SED model. We're getting a lot of weird images from me this week. When I Google searched dust in a galaxy, one of the things that came up was the space chicken. So this is an image of the space chicken. It's the running chicken nebula, I think, if you want to find more images of it. Maybe I beak. I don't know how you get running from this either. So if you can figure out where the running chicken is in this model, in this nebula, let me know. I'm very curious. I can't figure it out. But it's called the running chicken nebula, which is cute. And it has a lot of dust, both blocking and emitting light. So I thought it was a good thing to show as we start talking about why we would need to include dust in our SED models. So the first thing I want to talk about is absorption and extinction caused by dust. So dust is, like I said, dust is going to both block light and emit light. So we need to keep both of those we need to take both of those into account when we model our galaxy spectral energy distribution. In order to model extinction, we usually use an extinction curve. So this is going to be how much light do we expect the dust to block as a function of wavelength. And I'm showing a few different extinction curves here. They're going to depend on the size of the dust grain, the types of the dust grain, as well as how much dust is in a galaxy. So more dust and different types of dust will absorb more light, different light, depending on the size of the dust grain. So more dust, more extinction, bigger extinction curve, and we can kind of estimate the dust mass in a galaxy if we can get a nice SED fit. We figure out extinction curves by looking at stars in the Milky Way and the LMC, where we can actually resolve individual stars and estimate what we would expect their spectra to be based on their absorption lines using HR diagrams to get an unextinguished spectra, and then compare that to what we actually see, which is going to be a reddened extinguished spectra to determine how dust absorbs light in galaxies. So we're working with the assumption that dust in the Milky Way is a good model for dust in every other galaxy, which probably. Maybe high redshift galaxies have different dust, but it's probably not that different. So as good as a model as we can make using the Milky Way and the LMC, which are, now we've got Andromeda as well, but we're not going to resolve stars in any other galaxies. They're just too far away. Other things I wanted to point out here is this new measurement RV, which determines the strength of the extinction curve here. And RV is equal to the absorption in V band. So V band is in the Johnson-Cousins. We talked about our bands a while ago, but in Johnson-Cousins, there's UBVRI. So this is similar to G band in SDSS, slightly different, but kind of around the same wavelength range. So absorption that we see in the V band divided by the reddening parameter, EB minus V. So that's the extinction as a function of color, which is called the reddening. EB minus V is equal to the observed color minus the intrinsic color, using these B and V bands. So again, the magnitude in the B band minus the magnitude in the V band that we observe compared to what we would expect, the intrinsic, unreddened, no dust blocking color. We call it reddening because dust is going to block blue light more than it blocks the V light, the greenish light. So our color becomes less blue or redder. Yeah, and then absorption in V band is again going to be how many magnitudes are missing in V band because of dust absorption. So for the Milky Way, RV is about 3.1, so it's this black curve here. But depending on your galaxy, you could have more dust, you could have a lower RV, or you could have less dust and have a higher RV. And then what we're plotting here, so in this actual plot, what we're actually showing is the absorption as a function of wavelength divided by the V-band absorption. So one V-band would be here, and then we can see longer wavelengths. Sorry, this plot is backwards in my brain because it's lambda to the -1, so 1 over wavelength. This is how they always plot it. I'm sorry, but longer wavelengths are going to have less absorption. Longer, redder wavelengths, less absorption. Shorter wavelengths are going to have more dust absorption. And when you get to UV, dust is going to be pretty much blocking large fractions of the UV light we would expect to see from a galaxy. So
why do we have that particular bump at 2175 angstroms?
Good question. No one really knows, is the major answer. There's just a very large bump at 2,175 angstroms. It is called the 2,175 angstrom bump, and we don't 100% know why it's there, but we think it's probably caused by a specific form of graphite. So there's some dust structure that there must be a ton of it, some carbon lattice structure that a lot of the dust in the galaxy is made of, that just absorbs at this wavelength really, really well. It's not really correlated with the amount of emission from PAH grains we see. So it's not necessarily a PAH grain. There's still kind of questions about why we actually see this bump. But the idea is it is some form of dust that just blocks this wavelength really, really well. So when we make our SED fits, we need to take into account that light at 2,175 angstroms is going to be blocked more than we might expect if we just had a nice, smooth extinction curve. So any other questions about extinction curves? Other thing I want to point out a little is that there's kind of a difference between attenuation and extinction. So extinction is saying, like, if you have a big clump of dust, so this is a Bok globule, which is a dark cloud of dust that is completely blocking the light. So that is extinction. The dust blocks all of the light. We don't see it. We don't see especially the shorter wavelength light. But dust can also scatter light. So just like dust can block light, it can scatter light. And that actually can make things bluer. So if you think reflection nebula, if you think like the Pleiades, they look really blue because dust around those young stars is scattering that light into our line of sight. So that's going to be attenuation. Attenuation is going to include both blocked light and scattered light. Depending on where you are as an observer, you will see different things, and we need to take that into account. The extinction curves do take that into account. So when you have a dust cloud and you have light from stars, it's coming at us at all wavelengths. If you are looking through the dust cloud at the stars, you will see only red light. But if you are looking at the dust cloud kind of perpendicular to the stars, you'll see the blue light scattered from the stars. So kind of what we've got here is we have both a reflection nebula where we see blue light scattered into our line of sight, into what we see, as well as a Bok globule where all of the light is blocked. All of the blue light is being blocked by the dust between us and the young star. So also have to account for this in the extinction curves, that dust doesn't just block light, it also scatters light. So that's how dust is going to affect mostly the UV and optical light. As Ethan pointed out in the beginning, dust also emits as a black body. It emits light mostly in the infrared, as well as with the PAH features, the wobbles and the carbon structures that we call PAHs. And dust, for the main part, is the major emitter of infrared light in most galaxies. So this is a SED fit I did for one of the galaxies I work with. I don't remember which, but what it's showing here, the red light is going to be the observed light from this galaxy. The pink stars are my photometric data. So error bars in the sky are very large, which is only slightly concerning. But the point is, so we're fitting the photometric data to the red line. And the other thing this model points out, so this is a MagFizz model, we're going to be working with SIGAL, so what you'll see is slightly different. We're not working with MagFizz because MagFizz is a Fortran program and is therefore awful. But the blue light here is the unextinguished starlight. So if there was no dust in this galaxy, we would expect to see this blue curve. Because of dust, we instead see this red curve. The cool thing, one way we can kind of estimate how much dust is in a galaxy is by, or how much the optical and UV light is getting blocked. We use that attenuation curve, but we can also do some energy balancing by saying the amount of energy the dust emits should be equal to the amount of energy the dust absorbs. So dust isn't producing energy, it's not doing fusion, it's not gravitationally collapsing in on itself. There's no way for dust to produce energy if it's not absorbing that energy from starlight. So the amount of absorbed energy should be equal to the amount of emitted energy, which I know this little gap here does not look like it equals this huge amount of energy emitted over here. But that's because these are really short wavelengths. So what we have to remember is short wavelengths are going to be higher energy. So even though this doesn't look like a big amount of absorbed light, it's a lot of absorbed energy because it's almost exclusively UV and blue light that the dust is absorbing. So based on that, based on the amount of infrared light that we see, we can determine kind of what we would expect the galaxy to look like if there was no dust there. And we can get other cool things like a dust mass and a dust temperature based on our SED fits. And just a reminder, I'm not sure if I said this, I might have, but there's kind of two bits of dust absorption or dust emission we have to take into account. And that's going to be these chunky features from PAHs. So these guys in here, which are going to be from PAHs in the near and mid infrared, and then also the more black body radiation from large grains that's going to be in the far infrared. So this is 70 microns, 100 microns, 160 microns, and then 250 microns, which is what we will be looking at as well. Before we get to gas, any questions about dust emission? Or absorption? Cool. So the last thing we want to take into account is gas. Unfortunately, SED models do this very, very, very poorly. So pretty much anything an SED model is going to say about gas, you should take with a heaping spoonful of salt, because they don't really have the right tools to measure gas. And that's because the light we see from gas is going to be kind of, there's two ways that we might see light from gas in a galaxy spectrum. And that's going to be as emission and absorption lines, which if you're doing photometry, you're probably not getting light from individual lines. You're going to be getting light from a big chunk of wavelengths, not an individual wavelength. So you're not really measuring the flux of individual lines, which makes it hard for our SED fitters to really model these well. It needs to take them into account because it needs to know that some of my photometric band is going to include H alpha or something. So it's going to be brighter than we might expect if it did not include H alpha. But we're not getting the H alpha flux almost ever. We're getting the R band flux, which is also going to include a ton of light from old stars as well as light from hydrogen gas. So SEDs are not great at modeling emission lines for that reason, because we're just feeding it photometric data. We're feeding it these wide bands, not individual emission line bands. The other way gas might emit light is with free emission, so that bremsstrahlung scattering in as it bounces around as free electrons bump into each other. But this occurs mostly in the radio, and most SED fitting does not include radio light. And that's because radio observations are, you need an array typically. It's that really long wavelength, so you need something like ALMA or NOEMA, which are those arrays of dishes instead of one single telescope. So getting radio observations is a bit more tricky, and feeding that into a photometric code requires some kind of jumping through hoops that most people don't do. So most SED fitting kind of goes from UV to far infrared and doesn't include radio, which means that we're not modeling that free transitions either. So the two ways gas emits light aren't really going to be super important for SED fitting. So anything the SED fits tells you about the gas is probably going to be iffy. So that's something to keep in mind as we do SED fitting. But it is important that we do input these kind of emission line features and the free energy into our SED model, because there is light from gas in galaxies. So we need to take it into account, but how good our models are going to be is going to be hard to say based on the data we give our SED fitters. So very briefly, putting that all together, this is a kind of insane SED model that I'm showing here, but it's got everything we might expect. So we have stars. So this blue line here is the light we would expect from young OB stars. So part of our simple stellar population for young stars. They also, in this model, they have energy from older stars by this red line. So pretty much G and lower stars. So they have two stellar populations, a really young one dominated by O and B stars, as well as an older one dominated by lower mass stars. And we're adding those together to get all of our starlight. Then we've got nebular emission, gas emission as this yellow line. So we can see those really big emission lines from the gas, which we're taking into account, but how well we're modeling, who knows. And then they have a few different dust populations here. So this pink line is going to be dust in atomic gas, so kind of mid-temperature dust. Then we have a blue line for really hot dust, as well as a green line for cooler dust. So we have three different temperatures of dust that we're adding together to produce something that looks like a black body curve to measure here. And then the actual observed light for this galaxy would be this gray dotted line that you can only sort of barely see because everything else in this SED fit makes it kind of difficult, but it can see it's down here. So we've got some of our UV light is being absorbed by dust. This kind of shaded area is all absorbed, as well as some of the light from the older stars is being absorbed by the dust as well. So we can measure the energy absorbed by dust, the energy emitted by dust, what the PAH grains are doing, how many stars we expect there are, just all kinds of information we're getting from these SED fits based on the models we make of the dust emission, the dust absorption, and the starlight from our simple stellar populations. Okay, sorry. And just to point out what I think is kind of cool in this model, they show where different telescopes can actually observe these different bands. So JWST is going to look mainly in the infrared, but slightly kind of borderline optical. When it finally eventually launches someday, hopefully, Herschel, the telescope I use, which is now dead, unfortunately, was kind of our only way for getting these kind of far infrared emission lines. And then ALMA and SCUBA are two radio observatories. I think this is from a paper on SPICA, which is a potential space telescope that would be launched in 2032 and would look in the far infrared, which would be great for me because I like these kind of wavelengths. I think they're interesting, but right now we don't have a good way of measuring them. So I have done enough talking. Does anyone have any questions before I let you free to do some work on SEDs? Okay, so our big task for today is going to be looking at some SEDs that I have already made and just answering questions about them. So that is in your assignments in this SED Part 1 activity. What we're going to focus on for the next maybe 20 to 30 minutes is this understanding SEDs part. So this just has some questions about, like I said, some SED models that I made using MagFiz. So again, just a reminder, the red curve is going to be the observed emission. The blue curve is going to be the unattenuated starlight. So if there was no dust in this galaxy, we would see this blue line. Because there is dust, we see the red line. And then the pink stars are my data. So you're going to look at these, compare a few to answer some questions. There's a few things where I've kind of asked you to make predictions about how SED fits might make estimations about different properties of a galaxy. So those are things you might want to discuss together when I open up the breakout rooms and you work together. I'll also be jumping around if you have questions. So please ask if you do. And then the last question down here, question 7, asks for your group to come up with a research question that you think SED fits would be useful for. So something we could ask about galaxies that SED fits might help answer. So that's going to be the last thing you work on together. It doesn't need to be a great plan to start out with. I'm throwing you at this really early. So just something that you think maybe could be an interesting thing that we could investigate using SED fits of galaxies. Just have to clarify in my brain. Okay, cool. Both of those would be good things. But so cool. So using SED fits for different redshifts and seeing stellar populations. That's absolutely. So I can say really quickly what I use SED models for is I specifically look at how galaxies that have more dust attenuation vary. So I can go through and I can say which of my galaxies have the most dust attenuation, where am I seeing the biggest gap between my expected starlight and my emitted starlight, and how does that correlate with specifically how bright the C+ line is what I'm really interested in, but other properties as well. So there's all kinds of different questions we can ask, and like because SED models provide just a huge wealth of information about a galaxy, we can learn a lot from them. I can also just really quickly, just to kind of go through a few things. I know I talked with a lot of you about these, but in question 5, this was NGC 5866 was one of my few galaxies that actually had a pretty old population of stars. So what we're seeing here, this big drop off in the UV compared to the optical. So these are optical, these two down here are FUV and NUV. This huge drop off tells us there's pretty much no O and B stars. So this stellar population must be older, which means there's not really been a lot of recent star formation. So that's how you might get that data. question 6, I asked about the PAH features because I like PAH features. So the chunky features here are PAHs. And
Can you talk a little bit more about question 6?
So the features in the red line around 10 to the 1 micron, so it's these things here. So emission features, I think they're chunky because they're not tight lines, they're kind of bigger. And they're from the polycyclic aromatic hydrocarbons, so those very small dust grains in a galaxy. As they bend and wobble, they emit in these kind of chunky bands that we see. So we can use them to measure how many small dust grains we might expect. So if these kind of fluxes around the near infrared are higher, where there might be more PAHs, where if they're lower, there are fewer PAHs. So that's what's going on in there. But yeah, sorry, I kind of threw that out quick. The other thing, I think most of you got this, but the idea about how you can measure the stellar mass of a galaxy based on an SED fit is if we know how much light is being emitted by different types of stars, we can kind of say, okay, there's 10 O stars, which means there's this much stellar mass, and there's 50 G stars, which means there's about 50 solar masses, and we can add that up, sum all that up to get a stellar mass of our galaxy. So it's summing the amount of stars we would need of different classes to produce the starlight that we see in a galaxy. So that's question 3, I think. I think that hits at a lot of them. Like I said, please just don't feel like you have to finish this. Submit what you got through, but make sure you submit so I can actually see it. The last thing I want to talk about very, very quickly in the last 2 minutes is the other part of this assignment. I know you already have a lot to do for me, so I'm asking you to do one more thing before Thursday. I'm sorry, but it should not take very long at all, and that is downloading Seagal. So this is going to be the SED fitter that we're going to use. If you have a Mac, you can use this link to download the latest version here. It'll be a zipped folder that you'll have to unzip. It's going to be a lot faster if you can do it this way, so I encourage you to try to do it this way. If you are on a Windows, I know unzipping can be tricky, but you might want to try because the other option, which is another option for Windows, is you can download this Google Drive that I made that's just the Seagal data. So you'll just want to download this full drive, and it'll have everything you need to run Seagal. The problem is there's a lot of stuff here. I think it's something like 4,000 files. They're not very big, but there's 4,000 of them, which means it's going to take a while to download it. So you won't have to do anything besides push download, but your computer will, like it took me, I think 3 hours to upload everything. So I just had my computer running and I didn't do anything while it was doing that, but just know that that will take longer. So if you can do it from here, it's going to be faster. I'm sorry, Windows folks, it's zipped, it's compressed, which is why this is faster. And if you are on a Windows machine, you have to, I think, download an extra thing to uncompress things. So that's in this announcement, this link should tell you how to decompress things if you're getting frustrated with how long downloading the Google Drive takes, and you can use this instead, I believe. Please let me know if you have problems, and just let me know if you're able to get that downloaded. So next class, what I'll be doing is we'll talk more about SED fitting and how we can use it, but I'll also be just stepping you through how to run Seagal. So if you have it ready to go, you'll be able to walk through the steps with me instead of just watching, and then you'll pretty much have done like half of the spectroscopy project, which I'll talk about more on Thursday as well. So your next homework assignment will be pretty much 50% done if you're able to walk through that with me. So, okay, yeah, thank you, Thomas. So if you are on a Windows, you might want to grab the link that Thomas put in the chat. Sorry, I'm a Mac person. I'm used to this. But that's all I have for today. And I'm excited about grading all of your projects. You guys are doing awesome. Have a great rest of your Tuesday. Bye. Sorry.
Thank you.
Thank you.
I had a quick question about the project.
Uh-huh.